Okay, in the next part of this lecture, we're just going to do a little bit more on tactics, just give an overview of some new ones that are going to be useful in the coming proofs and things like that. The first one is COC has a bunch of meta-programming things, basically, which let you write yourself tactics and so on. The simplest form is this sort of, essentially it's a macro basically saying, well, I want to define this simple and try word to mean do a simple and then try C on all of the goals that result from the simplification. So you can just think of this as a simple macro where C here is a parameter, which itself is a tactic expression, basically. So we're not going to use that a lot in here, but you may find that if there's, a sequence of things that you do quite a bit in a proof, you may want to add a notation to make the proof a little bit easier to read. As it says in the comment here, there's a whole programming language called LTAC, and there's actually a few others that are more modern than that, which are ways to do more sophisticated tactic definitions. So they can do things like pattern matching on the goal state or on hypotheses, and they can do backtracking, so they can try things, and then if that doesn't work, go back and try something else. To a large part, we're not going to use those at all in this course, so you don't need to worry too much about it, but there's a whole level there that you can learn about if you're interested. The other level is if you really want to get into it, you can write tactics that are written in OCaml, which is the COC implementation level. So a lot of the tactics that we're using as a normal course of events, like induction and things, I believe are all written down at the OCaml level rather than in the LTAC sort of intermediate level. But basically, almost nobody writes those things except sort of super developers in the COC project. Okay, so just a few tactics that are of interest for actual proving things. We mentioned omega in a previous chapter briefly, but this is where we sort of say a bit more about what it is. So basically, if you have a goal like this in this little proof here, where the hypotheses and the goal sort of fit into this category of arithmetic, essentially formulae, which is mathematicians call it Pressburg arithmetic. So you add constants, numeric constants, you add addition, subtraction, and multiplication, and inequalities and equalities, and the obvious logical connectives, ands, ors, nots, and implies. It turns out that there's a decidable algorithm that can work out whether a goal holds or not in that subset of arithmetic. So that's quite a nice result. It's called the omega algorithm. So it's guaranteed to give you a yes or no answer if your problem fits into their subset. Okay, so in this particular proof, we could go through and use these facts here and do some manipulation to try and work out whether this is actually true. So this first one, we could probably work out that m is less than or equal to O by subtracting n from both sides. And this one over here, we could work out that O is equal to P, and then use that to derive that m is less than or equal to P. But omega knows how to do that automatically. So it saves you a lot of trouble in basic arithmetic sort of goals. So omega will just solve that immediately, which is much, much shorter than the obvious, the simpler steps of a basic proof for that result. So if you sort of remember what the subset is, you can try omega for these sorts of goals. If you have a subset that's not, if you have a goal that doesn't quite fit into the subset, omega will tell you that it can't it can't solve that system, basically. So you don't get a wrong result. You just get told it's not going to work. Okay, so the last part in this short section is just a list of some other tactics that we're going to see as we go along, some of which we've mentioned briefly in the past. So clear, sometimes in these bigger proofs you get a lot of hypotheses in the context of your proof state that maybe you don't need anymore and you want to get rid of them. So you can clear a hypothesis and then that just deletes it. The subst ones, often in these sorts of proofs, you end up with lots of goals that say, you know, x0 equals something, x1 equals something else, and then there's various appearances of x0 and x1 in the goal and in other hypotheses and things like that. And in theory, you can go through and do some rewrites to eliminate those just to simplify everything down or to essentially inline the variables. Subst will do that for you automatically. So if you say subst x, it will look for assumptions that say x equals something, or the other way around, and then just replace all the x's with the something and delete the x equals something hypothesis. So it's quite useful for simplifying the proof state so that you can sort of see more easily what's going on. We'll see examples of that as we go along. Subst x only does it for a single variable, whereas subst with no arguments does it for any variable that fits into this form. Sometimes you get an automatically generated name for something that you decide later you don't like, so you can use a rename to change its name. Not terribly useful because usually you can make the name appropriate by going back to where you introduced it and making a better choice at that point. Assumption we've seen, I think I've used that a few times. So basically if you have a goal and you have a hypothesis that is the same, you can just say assumption rather than saying apply H. And that's not a bad practice because it means that if the name H ever changes for some reason in the, you rearrange some part of your proof and the name changes from H1 to H3 or something, you don't need to change the proof because the assumption will find it anyway. Similarly with contradiction, if there's a hypothesis in the set in your current state that's equivalent to false, then it will find it and just dismiss the current goal. And you can do a similar thing by finding it yourself and then doing inversion on it or destruct or something. And constructor, we'll see constructor is more easily explained with an example, so I'll try and remember to do that as we go along. But basically it'll look at the current goal and it will try to find a constructor for the appropriate type that matches that goal. And if it can find a single one that works, in other words, there's not more than one, then it will apply it automatically. And again, the advantage is you don't have to mention the name of the constructor because it will automatically find it for you. A lot of these ones like assumption, contradiction, constructor are quite good when you're doing proof automation because it might be that in one, let's say assumption, it might be that in two sub-goals, the assumption you want to use is a different assumption. So the name H would be different in the two sub-goal contexts. But if you want to automate, you can use assumption to discharge both of those goals because it will find the appropriate one in each of the cases. So then the same proof, the assumption will work for the two goals. Whereas if you have to name the hypothesis, maybe the proofs are different because of the name. And the same with all of these. So constructor, for example, you might need to use a different constructor in a different case, but constructor, the tactic, will find the right one in both cases. So you don't have to explicitly apply the right one. So that can simplify the proofs. So don't worry too much if some of these are a bit unclear right now. We'll see, as they say, we'll see lots of examples as we go through. Okay, so I'll stop there on this piece and pick up with the evaluation as a relation in the next